Can you guys, am I coming through loud and clear?
Yes.
Okay. Yep. Okay. Great. Thank you. Thanks for the introduction. My name is Carrie Anderson. I'm very excited to be here today to talk to you guys about a remote sensing instrument for Venus that is currently under development. It's called V-Wishes. It operates in the sub-millimeter spectral regime at a very high spectral resolution. The resolving power is about 10 to the 6th. And the main science driver really for this instrument is really targeting and looking into key questions related to the chemistry and the dynamics that reside within Venus's middle atmosphere. And so there were some excellent talks yesterday about that. And so this instrument nicely complements that science that was discussed. Next slide, please. Thank you. All right, I just want to quickly give you an overview of the project. V-Wishes, it falls under the Matisse technology maturation effort, which is a Matisse. If those of you aren't familiar, Matisse is it's a ROSES program from NASA headquarters. It's 3 years, and really what you do is it's meant to mature a full system with an entry level of TRL4 to TRL6 for an exit level. And that's pretty much done by taking the instrument through TVAC or thermal vacuum at the end of the project tenure, which is what we're ramping up to do very soon. We've almost completed our 2nd year, and we should be going into TVAC later this fall, hopefully mid-October, give or take. And so V-Wishes, when we set out to do this, we were really looking into reducing the high swap nature of the instrument. And swap that's just size, weight, and power. And classic flight instruments like this that are a very high spectral resolution, operate in the sub-millimeter, these types of spectrometers are very mass and power hungry. And so we really wanted to reduce this aspect without sacrificing the science, because it's a fine line you tend to walk when you're looking at that trade-off. And we really wanted to make ourselves attractive to be picked up for as part of an instrument complement on a future mission to Venus. And so what we do is, we have that high spectral resolution, about 10 to the 6 I was telling you guys about, resolving power, but we also wanted to couple that with fairly broadband coverage. These types of flight instruments tend to have very narrow spectral coverage, and what they do is you resolve the line, and then you just go in and you look at specifically line by line by line. You tune across those lines. You don't get the continuum information, but because of the aerosol information in Venus's middle atmospheric region, the mesospheric region, I wanted to get some type of broadband coverage. And so we were able to work into our design 64 gigahertz of coverage, which is still pretty narrow. That translates to about 4 inverse centimeters in wave number space, but it's enough to get some information on the opacity from the aerosol. And really the way that the key enabling technology for this instrument really comes down to these digital spectrometer ASICs that we're implementing as part of the back-end design of our instrument. And so a single spectrometer ASIC, it draws it's about 4 gigahertz bandwidth, and it translates to about a 500 kilohertz spectral resolution, which is what that resolving power of 10 to the 6 translates to. And they each only draw about 1.5 watts. And so that's a game changer for these types of flight instruments. I mean, they tend to be pretty big beasts. At least think about like the Moreau instrument in the past. And the way we're actually doing this, rather than implement a ton of these ASICs, which will increase the power, we decided to go with 4 of the ASICs, so we get a 16 gigahertz instantaneous bandwidth. And then we essentially are going to be operating in kind of like a frequency switching scheme that we're still working out. That'll all come out in the calibration aspect of this, where we move and we grab 16 gigahertz of a different spectral range, and we do that 3 times, and then we reconstruct essentially the composite spectrum in the end to give us the full range, and I'll show you that in a minute. Okay, next slide, please. All right, so we saw this image on the right earlier, and this is from Vesper back in the 90s, and from Gordon Chin specifically. He's one of our science co-Is. And really what I want to show you here is just that the green rectangle demonstrates the vertical sounding range we're going to have with this instrument in Venus's middle atmosphere. And of course, in nadir mode, we'll be able to go a little bit deeper, but I would want to spend about 80% at least of the observing time in limb sounding mode. That's a great way to get vertical information immediately just from a single observation. And you can do that, you can scan Or you can do what's called a sit and stare or limb integration, where you center your field of view on a specific tangent height, and then you integrate. And so you get these very long path lengths, you integrate all those photons, and that's the way to really increase your signal. And on top of that, though, and that's just in the observing strategy, but on top of that, this instrument is very sensitive. And that really comes back to the heterodyne resolution. And what that means is that it becomes this powerful way to really pull out trace signatures from gases in the atmosphere. And so because of that, we can go and look into the chemistry, we can look at key compounds, carbon, water, of course, all the isotopologues, the main isotopologues at least, sulfur compounds, chlorine compounds. I'll show you in the next slide, I did a simulation to really emphasize this. The isotopologues are critical. We can look into the sulfur water chemistry, and we can also look for new compounds. And phosphine is a perfect example that I simulated to give you guys a sense of, there's one transition in our spectral range. On top of the chemistry, we can tackle pulling out wind speeds. We can pull out the velocities from the data, and that's strictly because of the high resolution, spectral resolution. You simply you're doing Doppler shifts to pull that information out. Next slide, please. Oh, yeah, right, this one. Okay, so I won't talk much about the science anymore, but you guys did a great job with your talks yesterday, so thank you for that. Here on the left-hand side, you can see these are all the compounds I put in the model. I did a simple rate transfer forward model simulation. That's all I did, trying to simulate what a V-WISH's observation would look like. And so what I did is I put the field of view, I centered it on 80-kilometer limb tangent height. So I'm integrating along that long, very long path of the atmosphere. I put the spacecraft 5,000 kilometers off the limb. We can, that's realistic, but we can put that anywhere. And I just assumed an instantaneous field of view of 3.5 milliradians. And I degraded the spectral resolution just a little bit to increase, so it wouldn't take so long computationally. And so what I've done is I've tried to color code the different transitions, and it might be hard to see on the slide, but everything on the left over there is in the model. And so things that kind of draw your attention to that big Wampen optically thick feature in the middle, that's water vapor. And then near about 577-ish, that's optically thick 12CO. Around 599, that's HDO. We'd get that very easily. And then something to draw your attention to on the lower frequency side, near about 533 gigahertz, you see that magenta line or curve really? Well, that's phosphine. And I had just assumed uniform distribution at 10 ppb, and you can see it's quite strong. And so that's partially due to the strong transition that we have of phosphine in this region, but also because I'm in limb sounding mode, which is what you want to do to increase that signal. And so we'll be able to detect this at much lower abundances as well, if indeed it resides at these altitude regions. Next, please. I won't spend too long here. I kind of already touched base on this, that we're also going after the dynamics, the complex dynamics in the middle atmosphere. What are the big drivers of the circulation? And really, that's just simply looking at the different zonal meridional wind velocities, once again, from the Doppler shift of the lines at this very, very high spectral resolution. And then we're also going to, map out part of like the first objective you saw on this last one. We're really looking at, what everyone's thinking about, what does the diverse climate at Venus reveal about Earth's vulnerability ultimately? And so that's kind of a thing we're thinking about going into this. And that really comes down to mapping out the spatial profiles and abundance of, well, first of all, the vertical temperature profiles will pull out all the gas abundances, the very trace compounds, and also the aerosol abundance, because we have that continuum region, that spectral coverage that we're going to get out of that. Next slide, please. Here, I just want to do another demonstration and expand on, I did this very quickly, but the 80-kilometer limb simulation you already saw, and I just want to do 3 other tangent heights. And so it's only a full spread of about 30 kilometers, but this is exactly what we'd expect with Venus. As you go deeper into the atmosphere, the pressure broadening, of course, kicks in and it gets more intense. And that's just demonstrating what the data would look like at those tangent heights. Next, please.
So can you start wrapping up now? You're running out of time.
Yes, I'm almost done. Thank you. I'm not going to go into this, but for any engineers out there, this is our system block diagram. And really the main point here is that there's multiple components under development in parallel, but we're coming to a point of fruition where we're going to be integrating all of these into a flat sat instrument and taking it into TVAC at the end of this calendar year. And then we'll bring it into my lab and we'll interface it with my gas cell system to simulate and validate, calibrate, and check the calibrations of our data processes. Okay, next, please. Just flip through these quick. There's like 3 in a row. This is just showing you what it would look like to get the 16 gigahertz. Next would be the next 16. We're going to go to the upper sideband next.
Carrie, 10 seconds here to wrap up.
Okay, just like hit 3 returns. Yeah, and there's a filter gap that's unavoidable. Next. I won't talk about these, but I'll just thank you and take questions.